Question: can you provide a detailed explanation of principal component analysis, PCA? Illustrate with clear examples and clarify whether rotation is necessary. Additionally, could you explain the potential consequences if PCA components aren't rotated? Answer: principal component analysis is a statistical technique widely used in machine learning and data analysis to reduce the dimensionality of large datasets, thereby simplifying data analysis while retaining most of the information. PCA transforms an original set of possibly correlated variables into a smaller set of linearly uncorrelated variables called principal components. Each principal component represents a combination of the original variables and captures a certain percentage of the dataset's variance. The first principal component captures the highest variance, the second captures the next highest, and so on. For instance, consider a dataset containing attributes such as height, weight, and shoe size of individuals, which are naturally correlated. Instead of analyzing these correlated variables individually, PCA can summarize them into fewer principal components. Perhaps the first component might represent an overall body size dimension, explaining much of the variance, and the second might capture a body shape dimension. Another example could involve financial data, such as stock market variables, including stock prices, trading volume, interest rates, and market volatility. PCA can combine these correlated variables into fewer principal components, such as one representing overall market performance and another capturing market volatility trends. Regarding rotation, yes, it is crucial to PCA, specifically orthogonal rotation methods like Varimax. Rotation in PCA simplifies interpretation by clearly differentiating components and maximizing the variance explained by each one. By rotating components, each principal component becomes more closely aligned with specific groups of original variables, making them easier to interpret practically. If components aren't rotated, we may end up with principal components that are not clearly defined, with overlapping variance between components, thus complicating the interpretation. Non-rotated components typically spread the variance more evenly, making it challenging to distinctly identify the influence or importance of specific variables. This lack of clear delineation may force analysts to rely on more components than necessary, diminishing PCA's effectiveness as a dimensionality reduction method. Therefore, employing rotation methods ensures each component distinctly captures unique variance aspects, significantly enhancing interpretability, analysis accuracy, and ultimately, data-driven decision-making.